Good evening, one and all present today with us. It is my privilege to welcome you all on behalf of NASNI as a coordinator, and I welcome you for the 12th talk of this year. Today we have with us Dr. Kandulapati Sriram. It is my great pleasure to welcome Dr. Kandulapati Sriram, Associate Professor in the Department of Astronomy at Osmania University, Hyderabad. Dr. Sriram is a distinguished astrophysicist whose research spans high energy astrophysics, black holes, neutron stars, active galactic nuclei, and stellar flares. He has made significant contributions using data from major space missions such as AstroSat, XMM, Newton, RXTE, and Integral. With more than 50 research publications in leading international journals, several prestigious research grants, and extensive experience in monitoring young researchers, Dr. Sriram has established himself as a leading expert in the study of accretion processes and compact objects in the universe. We are delighted to have him with us today and look forward to an enlightening and inspiring talk. Please join me in warmly welcoming Dr. Kandulapati Sriram.
I would like to, these are the characteristic properties of all these things. Okay. Now, this is a very famous diagram because you might have already heard many of the talks previously. This is known as HR diagram or Hertzsprung-Russell diagram. And you can see that 90% of the stars lies on this yellow patch along this line. Okay, and 10% of the stars, they are on the off diagonal paths and all these blue region part. This is basically this is the equation I was talking about. You can see the right hand side. It is absolute constant. Nothing you can't change nothing. I mean, H Planck constant, that is H bar, C or G. You cannot change anything. It requires 400 of physics because G comes into the picture because of the Newton. H bar is because of the quantum mechanics. MP is because of the quantum mechanics. C is the speed of light, which is again because of the quantum mechanics. So when Chandrasekhar derived it, it is of the order of 1.272 solar mass. But if you consider more advanced astrophysics, it comes out to be 1.4 solar mass.
Okay.
Okay. This is basically equation related to neutron stars. TOV is basically Tolman and Oppenheimer, and V is another person. I hope you might have seen last year one movie came, Oppenheimer. He is like the Manhattan Mission Project Director, but he also found this equation of state of neutron star, and he proved that the neutron star, the maximum mass of a neutron star cannot be more than 3 solar masses. Otherwise, it will eventually become a black hole. Okay, so this is one of the interesting studies. Okay, now I will skip this. Can you see my next slide? Neutron star pulsar.
Yes, sir. Yes, sir.
Yeah. So she's the lady, Jocelyn Bell, and his boss. So she was the first person. She was a scholar at that time. She was the first person. She detected something called neutron stars, and she found pulses, which is coming from one object. And if you see the periodicity of the pulsar, which happens to be 33 milliseconds, and these 33 milliseconds are considered to be the rotational speed of those pulses. And when you calculate those rotational speeds and using some classical formulas, you will see that the radius has to be of the order of 20 kilometers, and mass has to be of the order of less than 3 solar mass, and they term that as pulsars, which are basically neutron stars. So I happened to meet her in one of the conferences in 2014. I hope you can see my slide here. Can anybody confirm?
Yes, sir.
So the middle one is Jocelyn Bell, and the left side is Professor Sita, Dr. Sita from ISRO. I hope many of she is the mission. She was member in Chandrayaan. In MOM mission, she worked as the project director or assistant project director. So we had a chat at that time. Yeah, so this I will skip the part. These are small calculations. So yeah, now coming to the small black holes. Now I am on the slide of small black holes. So generally small black holes, the mass range is of the order of 10 solar mass or 20 solar masses. Okay, sometimes 30 solar masses. Right now we have a confirmation. We have more than 400 more than 400 number of small black holes which we detected in our galaxy. But the confirmation came for only 20 or 30, not more than that. When I say confirmation, confirmation means dynamical confirmation, that is using Kepler laws. The astronomers determine the masses of those binary system, and we confirm that these are actually stellar size mass black holes or 10 solar mass black holes. Actually, we detected 200, 300, but they are indirect methods by which we say that they are black holes. Theoretically speaking, we should see almost all 10 power 6 or let's say 1 million stellar size mass black holes in our galaxy. But we couldn't detect it because most of the time these black holes are in quiescent phase. Quiescent phase means they don't do any activity. They are very quiet. No radiation is coming. Nothing is coming out. Okay. Until unless nothing is coming out. And we know that one of the properties of black hole is they don't emit anything. So we are not able to find it. But according to simulations and all, you should have more than 10 power 6 stellar size mass black holes in our galaxy. As I said, it is very difficult to detect. And one more point is, if these black holes are in binary system, we can detect it. Okay. Our lives are very easy if they are in binary systems because the other star, there will be some matter which will be, because of its evolution, the other star will expand. The matter slowly falls into the black hole. And as the matter reaches to the black hole, it eventually emits X-rays. And we can detect X-rays and then we can study the various properties of this. And we can say they are black holes or not. But they are not active, so we have to wait. That's why whenever we go for the space observations, there is always something called all sky monitor with them. And this all sky monitor job is basically they scan the sky every 90 minutes or 2 hours, something like that. And whenever there is a X-ray, sudden X-ray burst or sudden X-ray observations, we use more high sensitive spatial telescopes to pinpoint that and we start studying them. So yeah, I don't know whether my animation is, can
It
you
is,
see my animations?
yes, yes, it is
Yeah, yeah.
working.
So you can see here what exactly happens. You have a star which is bulged, matter is leaving from that star. It is going towards a black hole. Of course, this is not a black hole, it's a neutron star simulation, but eventually you can consider that it is a black hole. The matter will form a disk, which we call as the accretion disk, and slowly the matter will fall onto the neutron star. If it is a neutron star, you can see beautiful pulses that at the dipoles you have beautiful pulses. Otherwise, it will simply go into the black hole and the matter will never come. Yeah. So now I've moved to my next slide. You can see these are basically some of the temporal variations of stellar size mass black holes in our galaxy. The name convention are also given. For example, on the left side, second panel, you can see XTEJ 1560 minus 564. This is the name of a black hole. And you can see that most of the time, the X-ray counts are very, very small. It's quiescent. It's very close to zero, so you don't expect anything. But sometimes you can see that the counts are suddenly raised 200, 300. Sometimes they are quiescent. Again, then there is a burst. So you can see that these are few of the black holes which I have shown, almost 6 black holes, light curves. We call it a light curves. So we have to continuously monitor. The basic problem with these black holes is we don't know when they are going to go for high X-ray radiations. So we generally continuously monitor them, and whenever there is a activity started, there will be multiple mails or electronic alarms in various observatories, space observatories. They go for it, they continue monitor it. Many of the astronomers write proposals to study them, and that's how we study the properties of these black holes. And so the beauty is, this is very slightly technical, but those who are from physics background and engineering background, they can understand that there is something called signal processing. So in my previous small animation, I've shown that as the matter approaches to the black hole or neutron star, the mass it forms a disk. It has an orbital velocity, and you can see that when you do something called Fourier peaks, okay, these are known as quasi-periodic oscillations. That is basically the matter is rapidly oscillating, okay, and you see the frequency of the out. It varies from 1 to 10 hertz. Again, by studying these oscillations, we can actually know whether it is a black hole or whether it is a neutron star. The problem, the X-ray view of neutron star and black hole is very similar. But if you do very sharp study of timing characteristics or spectral, like doing this neutron star or a black. So this is sometimes these oscillations appear and disappear very rapidly. Within few hundred seconds, they change. For example, in this slide, you can see there is a QPO here, there is oscillation here, and suddenly it disappeared. So this NQ means no QPO. So there was no QPO. And suddenly as the counts increased, you see a QPO. So there is a physics behind that, why it is happening, why it is not. But basically, if you try to understand this, you can actually know how the matter is behaving very close to these compact objects. Now coming to now, yeah, well and good. We know that there are stellar mass black holes. We don't have any problem. Okay. We have a very good physics with this. We know how these stellar size mass black holes come, how they are made, how they are produced. We have entire theory. Okay. There are some if and buts, but otherwise on a general scale, we know what is happening. Then there is actually supermassive black holes, which I'll come again later. But supermassive black holes, they exist. We know we have a dynamical confirmation because in 2020, Yazia's one lady and her group, they got Nobel Prize for that. They found supermassive black holes, dynamical confirmation of supermassive black holes at our Milky Way galaxy, which I think I've kept the animation. I'll show you. But in between these small black holes and supermassive black holes, there is something called intermediate mass black holes, and they are more elusive in nature because one of the methods says that they have to be intermediate solar mass black hole. When I say intermediate, that means their mass range has to be from, let's say, 500 solar mass to 10,000 solar mass. Okay, but they are very, very rare. We don't know why they are very rare, but they are very rare. And as I told you previously, that there are other methods to calculate the mass of the black holes. And I have written a very small formula, that is luminosity L is like 10 power 38 times of m by n square. Okay. So you simply, what we do is we try to measure the luminosity from the spectrum. We take a spectrum, we measure the luminosity. And if you know the luminosity, naturally you can calculate it. This is a very straightforward calculation. Generally, these intermediate mass black holes, which are also known as ULXs, ULX means ultra luminous X-ray sources. ULX means ultra luminous X-ray sources. They emit, their luminosities are very, very high, 10 power, sorry, 10 power 39 to 10 power 41. And if you keep these luminosities here, you will see that they will range from 100 to 10,000 solar mass black hole. Okay. Now the question is, where are they? Has there any observational evidence? Let me tell you, there is hardly any observational evidence which concretely say that there is intermediate mass black holes, but there are indirect evidence which I will show to you. So this is one of the galaxy. This is an interacting galaxy, and all these small dots, what you see, they are basically ULXs. ULXs again means they have very high luminosities. Okay, compared to stellar mass, they have high luminosities. And when you calculate their masses, they are of the order of 100 to 1000 or 2000, 3000 solar mass. Again, you see, this is one of the galaxy, and this is the central region, and this red dot is basically is one of the ULXs. Again, they claim that it is ULX primarily because of the X-ray luminosities. This is a typical spectrum what we often use. This is emitted by one of the famous source. I don't know whether I've written or not, but if you do the spectral modeling and all, they found that the luminosity is of the order of, I'm sorry, their luminosity is of the order of 2.3 into 10 power 41, and which amounts to a mass of the black hole, which is 2300 solar mass. We don't know whether there is actually a 2300 solar mass or there is some other physics going on, but this is most probable candidate for an intermediate mass black hole. Yeah. I hope my slides are moving, right? Can
Yes, sir.
anybody?
Yes.
Yeah, yeah.
Moving, sir.
Yeah. So this is a very small work which I done when I was an MSc student in the department. We told that there is no intermediate mass black hole. It is basically the geometry. Okay. So this is actually simple terms. You are not getting the luminosity of 10 power 41. It is actually the luminosity is beamed to you. So basically luminosity is less because it is beamed towards you. You will see a artificially enhanced luminosity. We did this geometrical calculation. We wrote a code. At that time, we wrote a code in C, which ran for, let's say, 2 days to get one curve. We took 2 days to get one curve. And we find that you can explain these luminosity difference. You can explain the luminosities, but if it is just 5 into the baseline of the luminosity, you can explain. If it is 100 times, even this model can't explain at that time. So this was very small MSc project, which, but of course, it came in a very reputed journal, ABJ, of it's in US based journal. Again, this is again a very famous source, intermediate mass black hole. This is known as Hollock's HLX X1. You can see generally these ULXs are off nuclear sources. So this is the galaxy, edge-on galaxy. This is the center of the galaxy, and it is very close to the center. Not so close, but we can say that. Okay. So this is one of the source. And this source, when you do that Fourier transformation or signaling, you will see beautiful QPOs. So just few slides back, I've shown you some quasi-periodic oscillation. These sources also exhibited quasi-periodic oscillation. And the beauty of this oscillation is that relativistically or classically, these can be connected to the mass of the black hole. Okay. And they found that for this particular source, M82X1, they found that the mass can range from 25 to 500 solar mass. Okay. This was very exciting news at that time. So this is again one of the methods by which uh, you can say that this particular source, that is M82X1, is a intermediate mass black hole. So it is a possibility. We don't know whether it is actually a 500 solar mass because we don't have any dynamical confirmation. We don't know whether there any optical counterpart. If it is an optical counterpart, how to find out what is the orbital period, etc., etc. It's very complicated. X-ray observations can directly came in Nature last year or last year. This is a you can see this is a cluster which is one of the biggest cluster in our galaxy. This is known as Omega Centauri. I'm sorry for the spelling mistake. This is Omega Centauri, and it's a very big cluster. It's a dense packed hundreds of thousands of stars. It generally these clusters are spherical in shape. They always stay very close to the galactic center, close to the galactic center. And it has been debated from last 2 decades or 3 decades. This particular cluster should enter. So you can see the vision. The entire this is the version. When you zoom it, so people said that there is that if there is a black hole at this part, at this, let me tell you, the size is very small. It's like one light year. So what they did was they done a very good. What they study, see black holes because it does not emit any light, but it has a gravity, and stars around it will experience the gravity. So they studied the stars which is very close to particular central shown in the. And this is the Hubble Space Telescope studied from 2002 to 2023. I cannot see it's 2000 or something. Yeah, 2002 to 2023. So this is the black hole. Now, if you carefully observe, you can see that 2023 there is a change in the position, star position, and then they perform all the calculations, and they found that, not going into the details, but they found that if the stars have changed its positions because of the black hole which is present, then the black hole mass should be of the order of 8,200 solar mass to 40,000 solar mass. Okay. So what basically they studied is the change in the position of these two stars, and they calculated something called escape velocity. Okay. And if they hello, shall I continue? Yeah, this blue
Yes, sir.
and
Yes,
here
sir.
black
Please
lines,
continue.
flat constant lines, are actually no black hole velocity. If there is no black hole and they are orbiting, that is this is a theoretical line. These stars, these magenta fast stars, when they observationally calculated, they found that the escape velocity of these stars are above 80 or 60. Okay. These curves, what you see, these curves, blue line and black dashed line, if you try to fit that, you have to fit at least the mass of the black hole has to be 8,200 to 40,000 solar mass. And this is a very strong, I mean, let's say this is the strongest observational evidence till now that there is a intermediate mass black hole which exists in our nature, and this will be one of the concrete evidence for the existence of the intermediate mass black hole. Let me tell you, if this group or any other group can confirm this, maybe after 10 years, this work can be nominated for the Nobel Prize. So that is the essence of this work. Okay. Still, there are some errors, but this is to date is the best example that there exists a intermediate mass black. Coming to the supermassive black holes, with so these are the galaxies, the size of the galaxy, and now we know that every galaxy we have a black hole whose mass is greater than 10 power 6 solar mass, 10 power 6 to 10 power 9, sometimes 10 power 11. So it ranges 1 million to 1 billion, like that. Now, how they came?
Not non-mobile ಅಲ್ಲ.
How they came? What is their formation technique, formation mechanism, at what redshift they form? I mean, at what, when the universe was young, what is the age of that universe when these supermassive black hole forms? All these are open questions. Nobody exactly knows. Some people say that they are primordial black holes. Primordial means they already exist in the universe, and somehow matter came to it, and all this galaxy formation came into the picture. But exactly we don't know. Okay. So this is a very famous source, 3C273. You see that this is Cygnus A. This central region is the visible galaxy. See, this is the visible galaxy. I'm talking about galaxy, not even talking about supermassive black hole, which will be somewhere at the center of this source. Supermassive black holes are very dense objects. They occupy very small region of not even 1%. Let me tell you, not even 1%. And but its activity is so huge. So this is the entire galaxy. and these are the radio lobes. So the idea is that some activity very close to the supermassive black hole is emitting lots of jets, lots of flows out. So they are going outward. They are hydrogen gas, which is all represented here. It is ionizing. That's why these you see as hot logs, which can be detected in radio, not in any other. And there are good, you can say, small jets like structure. So matter is a jet like structure. So they are enigmatic. Without black holes, let me tell you, you cannot have star formation in a galaxy. There will be no activity. So actually, black holes are good because they help us to they help in forming a star or star birth take place. Now, how to know the mass of the black hole? Now this is I don't know. Can you see the animation? It is running now.
Yes, sir.
Yes, yes. Yes.
Yeah. This is a Milky Way which we are right now watching. And now we have a more advanced animation, but these are all real observations. Okay. So what you have observed is that the observation started 92 uh, to the center, which is located in the Sagittarius A. So that plus supermassive black hole. So what we study is we study these star orbits. For example, this particular star, there is a complete orbit. So we try to measure A, that is semi-major axis on this orbit. We measure the time for particularly this star. If I remember, it is 15 years. We know semi-major axis. We know its eccentricity. We simply use Kepler's law, and we found that Milky Way center, the supermassive black hole mass is of the order of 4 million solar mass, 4 into 10 power 6 solar mass. And for this work, Gezas and her team in 2020, if I'm right, they got Nobel Prizes for it. This is the first dynamical confirmation that supermassive black hole exists. Of course, for other galaxies, we cannot do or cannot perform such kind of studies because your resolution has to be very, very high. Even with 100-meter or 200-meter telescope also cannot do that. So we have to rely on some other methods. What is the other method? One of the method is this is a typical spectrum of AGN, or you say typically for very active black holes or active galaxies, you will see many lines: carbon line, magnesium line, oxygen lines, H alpha lines. We try to study the width of these lines, and by measuring the width of these lines, we can know what is the mass. These are my works in 2022, 2023. We studied almost 3,000 AGNs, active galactic nuclei, that is basically supermassive black holes, where a lot of X-ray emissions or optical emissions are coming. And we analyzed almost 15,000 spectral lines, and we determined the mass of the black hole, and we studied various parameters of those galaxies or activity. And so we measure these lines with, if you do proper modeling of the spectrum, we can actually measure the masses of those black holes. This is again another method, but this is very complicated, but I don't want to continue. But this also I work, this is known as, again, by doing the cross spectral density and all, we can again study these masses. Yeah, this is my recent work, which actually came in. This is like discovery and ultra fast outflow. You have in one of the galaxy in IRS 97, etc. Recent work, it got media attention also recently. And what we found, if you carefully see, this is a spectrum of that particular galaxy or galactic nuclei, central region of the. We see these two lines. Okay, one line is at 8 kV, line is 0.5 kV, and actually these should occur at 6.97. That's what I have written. They should occur at 6.97 keV. but we are 8K. Blue shift some energy, and it is we as that these lines actually, blue shift, something called red shift, and it got blue shifted because there is a strong wind which is present in this particular source. So it was not discovered earlier. Suddenly we were lucky to get away from when we got the result, we actually were surprised actually how this piece of information we immediately to journal ABG, and in 20 days we got this acceptance from the journal. Yes, there is a discovery event of. And the more interesting point is that this is 2005 observation. You can see these two lines, whereas in 2019 observation, there is nine actually. There is nothing. I mean, one can argue this. There is a one single point, but we don't rely on single points. So that means that winds are changing, the speed, the outflow decreased because of some mechanism. Still, we don't know what happened to that. We have a sudden disappearance. A sudden, we can see here from 2000 to 2019 years, and cosmic time scale, 14 years is very short time. So we are studying on why this happened, why suddenly the outflows have disappeared. And let me, these outflows are important for star formation. If you don't have outflows, the star formation is very small. This is a typical optical image of this particular source where we just, I want to show that this is the optical image, and generally they keep a slit here, and by analyzing the spectrum we can know the mass. This is because the mass of this mass of a Milky Way black hole, they are same. When we measure the mass of this is the order of 6 into 10 power 6, whereas our Milky Way mass is 4 into 10 power 6. So they are sort of course, we also detected these blue shifted lines in soft X-rays also. Like this is 1 point. We have sees at 1.3 keV. This line should be somewhere 1.2 keV, not shifted. Okay, and that the they are with speeds of 30% of the speed of light. So the wind very fast, 30% of speed of very fast, 60,000 kilometers per second. Into 2009, okay, this particular line is again disappearing. So take this is I have written workshop. So this is a very fascinating subject. Any youngster can work on this field. There is an Indian satellite also, which is studying, which is known as Astro, which is still working in space and giving lots of data. And the data is open to public. Anybody can present all those things. Yeah, thanks. So here I will talk. Thank you very much.
Thank you very much, Dr. Sriram, for this exciting talk regarding all types of black holes. Now,
Thank you.
before going ahead, we invite all the for their questions or queries regarding this.
Sure. Yeah.
Sir, is a black hole some kind of a...
No. The basic difference between a black hole and a wormhole is black hole absorbs, it doesn't absorb. Whatever fall into this black hole will never come out. It absorbs, okay? White hole is something which is ejecting matter away out.
Yeah.
Okay. And one more point about wormhole is that wormhole is a theoretical object. Nobody has observed wormholes yet. A study which says that wormholes, even if they exist, they are very unstable objects. Within universe timescale, they will disappear. disappear.
Oh,
Okay, so have any observational proof that there are wormholes? But we proves where we have black holes. Answer.
what gives them the thrust?
Purely speaking, madam, we don't know the exact physics. There are probably one very strong thing is that as the matter has something called magnetic field of lines, which are vertical in nature. Somehow this accreting material, they allow to this magnetic field of lines. And there is a theory which says takes the angular momentum from the spin of the black holes. Because these
Okay.
supermassive black holes are black and their relativistic spin or of light. So these matter, these magnetic fields along the matter, they take some of the momentum from that magnetic field of lines and they shoot out as jets. And their speeds are enormous. They are relativistic, sometimes 99%. This is really,
Okay.
yeah. No, black hole doesn't have any magnetic field or electric field. Matter is nearby. The matter which is nearby, they have magnetic fields.
Okay.
My mind is that one side we say that nothing can come out from black hole, and other side
Yeah.
we say some jets are emitted by black hole.
Black hole. Jets are not emitted by a black hole. Jets are something very close to the black hole. And the matter which is interact and exchange this black hole. Nothing is coming out of the black hole. Jets are very close to the black hole. That's what I'm saying.
Okay.
Uh, we know about that is X, Y space at
Yeah.
time. Does that mean that the black hole is having some fifth dimension also?
Madam, theoretically, we have many dimensions. 11.
Yeah.
But the problem, that is the biggest challenge we have. As you said, observationally, we don't know about other dimensions. They are very, very small as per the string theory. We don't have any observational proof for that.
Okay.
Right.
Thank you.
Thank you.
Any other question?
Sir, is a white holes?
I told white holes or worlds, they are theoretical objects. They are used for conserving the black hole. Okay. Because we want to satisfy the matrix. So that eventually led us to something called wormholes or white holes. But the problem is, first problem is we have never observed any white holes or wormholes. Second is some work, research work done in wormholes, which says that they are not stabilized objects. Okay, even if they exist, they will they will not be stable and they will collapse. So we don't have any observed evidence of wormholes.
Okay, sir.
Black hole shrink? No, sir. Black hole cannot shrink. As per the Stephen Hawking area theorem, whatever the matter goes inside, its job is to increase the area of the black hole. So the black hole once formed and is more, the mass has to be more. It will increase, not decrease. This is the famous Stephen Hawking area theorem, which doesn't allow it to shrink.
Do we have an idea that what is the mass of a black hole?
Yes, we have. Stellar mass black hole masses, we have dynamically confirmed, for which Nobel Prize was given. For Milky Way center supermassive black hole, we have dynamical confirmation that it is a mass of 4 into 10 power 6. So we have measured it. We know what are the masses of these black holes. So very high precision.
So now I invite Dr. P.K. Aluwali sir for yes, sir. Please.
First of all, greetings from Indian Association of Physics Teachers. Thank you very much for sparing your time.
Thank you, sir.
Because what we feel is that through this effort, we are creating a resource for a community of physics students and teachers so that they can understand various aspects of the astronomical problems which are being studied at present and the excitement around them. And I would be very happy to tell you that last year, when we ended this series, we published a small booklet thanks to Professor Hemant, called Cosmic Conversations. And in each page, we had provided a QR code for watching the uh, YouTube link itself. So this is the idea behind this, because there are certain things which are happening around in the country which are very exciting, particularly with the coming up of 4-year research degree program at undergraduate level. We find that we have to tell our students and teachers what are the possible projects which they can do. And today, when you gave that task as task for home, I think that was in that spirit only.
Yeah.
I really loved it. I really loved it when you said that. And
To add these points, let me tell you, sir.
yes.
I heard Kasturi Rangan sir speaking in one of the occasion, and he told that the space science is going to be the next big science. Let's say at
Yes.
least for next 500 years. And you can see how the space tech companies are mushrooming throughout the world. At Hyderabad itself, we have 5 space tech companies. Of course,
Yes.
right now they are not doing any astronomy or space science, but it has started. Let me tell you, 20 years back, if you see all the IITs, there is no astronomy in IITs 20 years back. Now, if you go to any IIT, NITs, ISERs, any national institute, there is always a astronomy department or space science department. So it's
Yes.
a next big thing, or because astronomy is not a subject by itself. We require maths, physics, software, computer science, electronics, mechanical engineering, electrical engineers. Everybody, if they feed it, then you can make your instrument, and that instrument has to be flown out. And then you study various sun or any other thing. One of my friend who recently visited from NASA to Osmania University. So I was talking about that. What is the next decade big science what NASA is planning? And he was told that it is the space science or space weather, something we call space weather. Then the reason he told was very exciting because now everybody want to go to space.
Yes.
Everybody, why not for doing science? Science is the second thing. The primary thing is tourism. They want to establish for Elon Musk want to put a mobile tower on moon. Everybody will do that. It will be like, after if you have a very good technology in space, within Earth through 3 orbits again come back. So with that sense, that's very good topic. So space weather is going to be a very big thing. So already India is working on it. Already there is a space mission called Aditya, which is studying all these things.
Yes.
But for
Yes.
youngsters, space science is going to become a very big job opportunity, not in government sectors. That's why ISRO has planned space technologies private. 2-3 years back, they have given go for privatization. ISRO cannot. ISRO has to think after 100 years. Right now, go for privatization. That means all the rocket launching, etc. They
Yeah.
all the youngsters, so those who are doing, they can do it. Second
Yes.
point,
Yes.
what I want to know, most of the
Most of the
astronomical
astronomical
data
data
is public
is
domain.
public domain.
Fine. So thank you very much, Dr. Sriram, for enlightening on this. And there is one take which I really would really mention here, as you brought in the name of Professor Kasturi Rangan. He was, in fact, the architect of the new education policy. He was the chairperson of that group which formulated the national education policy. And I think his stamp is visible in that when we look at the way research has been made part of the undergraduate curriculum itself. And I think the talks, the way you have presented today, these are very exciting topics. And I remember you brought in Professor Chandrasekhar's name, and he had written a great book on black holes, which is a kind of a masterpiece. And I think this is very exciting if we can really continue with these kinds of seminars, stealing your time to come to us and enlighten our students. So please don't worry about the audience may be less, but our purpose gets served a lot because there are lots of hits which happen when this lecture gets posted on the YouTube channel of NASNI itself. So once again, I thank you very much on behalf of IAPT. Hope you will keep on obliging us in future also. Thank you
Sure,
very
sure.
much.
Thank you. Thank you for the invitation.
very much,
And
sir.
I think I readily accepted the invitation. And
Yes.
what I want to point out that number of participants are not less, sir. I have given a talk in Japan. There was only 2 participants at that time. So it is
Mhm.
not the participant. Participant is curious as to listen to you or not. That is much more important.
Yes, yes,
Even for one student also, if he listens, I will give
yes,
a talk.
yes, yes, yes.
So
And
participants, number of participants, they are very healthy. Like I can see 20. So they are
yes,
very
yes,
healthy
yes.
for me.
S. Chandrasekhar taught 2 students who later
Yeah,
won
yeah.
Nobel Prize before him. And
Yes,
he used
yes,
to go, I think, 100 miles to teach them.
yes, yes.
So thank you very much. Great.
Thank you, Aliwal. So thank you,
Thank you
Hemant
very much,
sir,
sir.
Kulkarni.
Thank you very much, sir. Now, Dr. Kulkarni, can you hear us?
I,
Yes, yes, please.
it is unfortunate I missed Dr. Sriram's presentation because of some technical issue. I moved my place about a furlong away and I had some difficulty. Last 10 minutes I could get, but I will see the video and comment on that, okay? It's a great thing that Dr. Sriram came and addressed our gathering, and I'm very happy about it. I think this way I was particularly happy to introduce because I studied in the same institution that he is studying and he's working, and I missed the pleasure. But in any case, the lecture was good, and I will see the thing later. Thank you very much, Dr. Sriram, and everyone else. Thank you.
Thank you. Thank you very much, sir. Thank you.
Thank you, Kulkarni sir.
Yeah, thank you.
So, finally, on behalf of NASNI, I extend heartfelt thanks to Dr. Sri Ram for sparing time and for telling us about unrevealing mysteries of black holes. Earlier, I heard only black hole. Now, today, I also know small, intermediate, big, and big black holes. They have also different categories. And you have explained all intricacies of these black holes, sir. And it is as Dr. Aluwalia sir told, that it is a big resource for our IAPT, which you have given us. And thank you very much. Thanks to Dr. Aluwalia sir, Dr. Kulkarni, Madam Deka, Madam Amoli, and all Dr. Pranita. Thank you very much. Thank you all.
Thank you very much, sir. I,
sir,
I,
I would
I
like
love to
to,
give another talk on some other topic. No issue.
Thank you so much.
yeah.
Thank you so much, sir.
Thank you. Bye.
Now we sign
Hemant
off.
sir, I would
Yes,
just like to add one more thing.
yes,
I think
please.
so for the topics like the black holes or any other topics, I think so one session is not at all enough. We want some more sessions on the same topic so that we
Okay.
can get deep dive into the information.
Right, right. Okay. We will try, madam. Yes. Thank you very much. Thank you. Thank you all. Good night.